So I'm very happy to be here at Perimeter, one of my favorite institutions in theoretical physics in the world. I'm particularly happy that I'm talking during this year of the 25th anniversary of Perimeter Institute. Today I'll talk about new physics, in particular how we've been doing research during the last century and what I see as going forward in the next few decades. Most of what we've learned in new physics in the past 80 years has been research done in big collaborations. Now we are transitioning to a new era when research done in smaller collaborations, in smaller groups, promises to give us fundamental answers to new physics that we haven't had before. What I want to do is to explain this transition and also point out some very exciting questions that may be answered in this process. I will start with some basics, which is, what is physics? Physics, first of all, comes from the word physis, which in Greek means nature. So the objective of physics is to build one theory that explains everything in the universe. Physics is using two major tools to do that. One is mathematics, and the other is experiment. Both of them equally important. Mathematics is simply the expression of physical laws in mathematical formulae. And the purpose of experiment is to figure out what's actually true by observation. So it's a very simple strategy for how to find out what is truth. Now I want to discuss a bit about both components, both theory and experiment. The realization that mathematics is relevant to nature goes back to the Pythagoreans. And in particular, the Pythagoreans used to say Theos ai geometry, which means God geometrizes everything. So if you wish, a modern paraphrase would be God uses mathematics to describe nature. This belief went down to Plato, who was a student of the Pythagorean school. So when he built his academy, the Academy of Athens, the first university, he had an inscription outside the door saying that no one ignorant of geometry should enter. There is a somewhat more polite version of this in the entrance of Perimeter Institute, which you can all read. I won't actually translate it because it's not polite enough, but so this interplay between mathematics and nature has fascinated humanity since the Pythagoreans, like 500 years BC. And one of the nicest comments on it that I have read is by Eugene Wigner. Eugene Wigner in 1960 wrote a very nice essay called The Unreasonable Effectiveness of Mathematics in Describing Nature. There he said, mathematics is a wonderful gift which we neither understand nor deserve. And this is a very deep statement. I want to dwell a bit why it's so mysterious. The connection, first of all, the connection of mathematics and nature is a big question mark. Why does nature use the language of mathematics? What is also an amazing coincidence, that's the gift part, is that we, tiny human beings on a tiny rock in a vast universe, can understand mathematics, can understand the language of nature to such a degree that we can think in our labs or in our offices and write down equations and figure out what happens everywhere in the universe. The models that I'm going to talk about apply everywhere in the universe. So it is a complete lucky coincidence that mathematics describes nature and we're just barely smart enough to understand enough mathematics to understand at least some aspects of nature. Now, mathematics is so powerful. It's not really, people usually say, oh, it's the language of physics. It's not just language. It is like having an extremely powerful friend. If you give him the right rules and you ask a well-defined question, it's a very powerful friend. It will give you the answer. The more precise the question, the more precise answer you'll get. So it's a miraculous tool. It's divine, and the power of mathematics has led physicists to idolize mathematics, and the public at large idealize. When people usually talk about physics, they have mathematicians in mind or mathematics in mind. Yet there is an equally important part, which is the experiment. And the experiment has the last say. This has been said beautifully by Richard Feynman, who back in '64 said, it doesn't matter how beautiful your theory is, it doesn't matter how smart you are, if it doesn't agree with the experiment, it's wrong. And it captures the essence of how important experiment is. And of course, physics without experiment doesn't really describe nature. Experiment without mathematics is a chaos. You might as well collect all the data and all the lab books of the last 2,500 years, put them in a big computer and call it physics. Physics is much more than that. The key point that mathematics allows us to use is a few precise rules from which you can derive everything. A few equations from which you can derive everything, and in principle, you can derive them to arbitrary precision. And if you can measure them to arbitrary precision, you have an amazing coincidence that the two should agree. Now, experiment, in fact, is as old as theory. The ancients, around the same time when the Pythagoreans were thinking that math is the language of nature, were also doing experiments. And here you see, on the left, you see Archimedes. So Archimedes, when he was 22 years old, he was tasked by the king to determine if his hat was made out of gold. His crown was made out of gold, okay, 100% gold. So Archimedes had to solve this problem, and he got the idea when he was entering the bathtub, when he noticed that the more he immersed himself, the more the level of water was raised. And then he made the brilliant hypothesis that perhaps the amount of volume displaced when he immerses the crown in the water, he can figure out by just figuring out the volume of the water. So an irregular shaped object like a crown, he could determine precisely the volume of that. He used that, and eventually it turned out it had some silver in it, the crown, so the person went to jail. The person who built the crown went to jail. And another famous story is when he made this realization, which was, he got so excited he jumped out of the tub, and I come from California, of the tub, and was running around nude in the streets saying, "Eureka, Eureka," which means I found it. Similar Eratosthenes. Eratosthenes was the first person who figured out, by looking at the difference in the size of shadows in two different cities separated by 800 kilometers, Syene and Alexandria, by figuring out the difference in length of shadows at the same time, he was able to determine that the Earth is round. And he even estimated, turns out quite precisely, the radius, the circumference of the Earth to be about 40 million meters. And this was done, of course, 2,400 years before the flat earthers of our times. Notice, both of these people are actually were mathematicians. Archimedes was a famous mathematician. He actually independently invented calculus. Newton was also a theoretician, and he also did experiments, just like Archimedes and Eratosthenes. Here he's pictured doing experiments in optics. And a counterexample to this rule that theorists doing mathematics was Faraday. Faraday was not from the British aristocracy, so he didn't go to Eton, so he didn't learn calculus, and he didn't learn trigonometry. And he was complaining that he wasn't well equipped to do physics, but he was arguably the greatest experimentalist, one of the greatest of all times. He discovered many, many aspects of electricity and magnetism. The way he figured things out, he was very intuitive. He introduced the concept of field, which is now very popular, an entity that permeates space, and that allowed him to build intuition and without math to figure out what experiments to do. So 3 of these people are theorists. It's very odd to see Newton doing experiments. He's considered the greatest theorist ever. And in fact, he was a very dedicated experimentalist. In fact, he was so dedicated that he wasn't just an experimentalist. He would act as experimental equipment, his own self. So he's famous for doing experiments in optics, sticking a needle under his eye and moving it around to figure out the laws of optics and also the physiology of the eye and things like that. So these are examples of early-ish experimenters, that some of which were also theorists, and that was very traditional. In fact, until the 1940s, many of the great physicists like Fermi, Felix Bloch, etc., were both theorists and experimentalists at the same time. Now, so this is all of these experiments that I showed are small-scale experiments. They were in a room or in a small amount of space. The transition to the big science era started with the Manhattan Project in 1945. That's when the public realized that science is important, and a lot of funding started coming into science. As a result, we started building bigger and bigger projects. So what used to be tabletop experiments, this is what's called an accelerator, or sometimes it's called a collider, collides elementary particles. So accelerator started out being palm-sized object, then tabletop, and now the biggest accelerator in the world, which is the Large Hadron Collider in Geneva, Switzerland, is 27 kilometers around. And it completed, the Large Hadron Collider completed what is called the standard model of particle physics. In other words, as we went to higher and higher energies, we studied phenomena. We needed bigger and bigger accelerators, and we studied phenomena involving more and more subnuclear constituents, elementary particles. So this gave rise to the standard model. The nicest way to show the standard model actually comes from a movie called Particle Fever, which sort of gives you an idea of the various constituents of the standard model, the components of the standard model. The things in the middle are forces or particles that mediate forces. So this is the gluon, which glues together the components of the atomic nucleus. W and Z are particles they are called weak interactions. They are responsible for radioactivity. Gamma is the photon, is the particle of light that we are all very familiar with. Then there is gravity, so these are all forces. And outside on the perimeter, you see the red things are subnuclear particles. For example, D and S are called quarks. They are inside the nucleus, and the others are heavy brothers of the down and strange. The up and down quarks. And the greens are brothers of the electron, okay? Heavier versions of the electron or very light versions, relatives of the electron. If you count, you have roughly 20 particles and roughly 12 plus 6 particles and roughly 20 parameters in the standard model. So in terms of 20 particles and 20 parameters, you explain, as far as we know, almost everything that we observe in the universe, and I elaborate on the almost. The range of validity of the standard model is enormous. It covers over 40 orders of magnitude. It can explain things all the way from subatomic distances, all the way to galaxies and the universe as a whole. So the standard model, as far as we know, applies in almost all phenomena, with one exception that I'll come to, which is called the dark matter. It's an incredibly successful theory in many ways. It has been tested with literally hundreds of measurements. And the most impressive success of the standard model is in predicting a quantity which is called the gyromagnetic ratio of the electron. This is essentially, it measures how rapidly an electron precesses in a magnetic field. It's an important quantity, and to figure it out, first of all, the theoretical calculation is very involved, and you can carry out the theoretical calculation to the point where you can make a prediction about the magnitude of this quantity to 1 part per trillion. Extreme precision. This means 12 decimal decimal places precision. Experiments over the years have been trying to measure it better and better. The latest, going back to 23, is that you can measure this quantity to a precision of 0.1 parts per trillion, which is like 13 decimals. An experiment and theory agree to that precision. And this is an astonishing thing, to be able to have something, a theory that comes from your mind, agree with experiment, where you go out and find out what nature is actually doing, to that 12 decimal places, is an astonishing accomplishment. It's one of the greatest accomplishments of physics, and it underlines how important the standard model is, and how fortunate we are to live in a time where it has been confirmed. It took roughly, depending on when you start your clock, a century to develop it slowly, and then after the Manhattan Project, the progress came very fast. So this is both the range of validity of the standard model and the precision with which it has been tested in some cases, like in atomic phenomena, like the one I'm talking about now, is incredible. So why do we not stop? If the standard model is so great, such a great theory. A few reasons. One is that we know there is some extra stuff out there. In particular, there is something called dark matter. Ordinary matter, what we are made out of, is only 5% of the energy of the universe. There is dark matter, which is 5 times more than ordinary matter. Dark matter is called dark because we cannot see it with our eyes. Dark matter doesn't emit light, doesn't radiate light, so we cannot see it, but we know it's there because we can measure its gravitational influence on stellar objects. And then in addition, there is dark energy that I'll say a few things about in a moment. Second reason why we want to go beyond the standard model is 20 parameters and 20 particles is very impressive considering the range of phenomena that you describe. But it's still too much. If it's really fundamental, you would think that, oh, maybe a truly fundamental theory should have, one parameter and maybe fewer particles. So it sounds like we can economize more and have a more elegant, a more simpler theory. Then there is 2 outstanding problems, which I'll come back to a couple of times. One is called the cosmological constant problem, which essentially is the question of how come the universe is so big. Turns out there is a quantity called the dark energy, which we know is the significant portion of the energy, the dominant portion of the energy of the universe. This dark energy, which is essentially the energy density of the universe, right? So this dark energy, in the standard model, its natural value would be so large that the universe would only grow to be about 1 millimeter. Okay? So in the standard model, the natural expectation for the value of the dark energy is such that the universe wouldn't grow beyond 1 millimeter. To make the universe much bigger, you have to tweak the theory, fine-tune some parameter of the theory to an incredible precision, 100 decimals or so precision, and then you can have a large enough universe. So that's called the cosmological constant problem. It is quantitatively the most important problem that we face today. And then there is the hierarchy problem. The hierarchy problem is simply the question that of why gravity so weak. Why is gravity so weak compared to the other forces of nature, like electricity? And here I can do an experiment to demonstrate the weakness of gravity. And here is the experiment. When I lift my arm, the atomic forces on my shoulder are able to overcome the gravitational attraction of the entire planet Earth. The gravitational attraction of the entire planet Earth on my arm is compensated for by the atomic forces that are acting on my shoulder. Atomic forces, which are in essence are electrical forces. So the electrical forces of my shoulder overcome the gravity of the entire Earth. That only happens because gravity is intrinsically much, much, much weaker than electricity. And this is a very subtle effect. We usually think, oh, gravity is not very small, simply because gravity always acts one way, it always attracts. Electricity sometimes attracts, sometimes repels, so there is some cancellation of attraction and repulsion. So we don't realize it, but that is an outstanding problem. This problem is probably the second most important problem in physics. It's easier than the first, so it has had several approaches that are being tested in the lab, and I'll talk about some of them. Okay, so now we go back to the drawing board and we want to build a theory beyond the standard model. What principles do we follow to build a theory? we want to follow the same principles that led us to the Standard Model. And the first principle, the most fundamental, is the principle of minimalism. Minimalism goes back to a priest called William of Ockham, who stated that essentially the principle of minimality, that we shouldn't add more components to our theory than are necessary. The most minimal amount of ingredients we should add to our theory. So this is called Occam's razor, and it underlies much of the physics that we've been doing over the last centuries, since the 13th century, when Occam pointed this principle. In modern physics, the way we implement Occam's razor is mostly through something called unification. Unification is the idea that two very different phenomena are explainable by one and the same principle. For example, Newton in the 17th century was able to unify celestial and terrestrial phenomena. Now, before Newton, most people thought that terrestrial and celestial phenomena are on totally different grounds. Terrestrial phenomena is something that perhaps the human brain can comprehend. Celestial phenomena, they need gods pulling the planets or angels pushing on, etc. So they thought that it was a different domain, that the two were unrelated. It was Newton who, in his universal theory of gravitation, showed that the way that an apple falls and the way that planets move around the sun are described by exactly the same equations. And this was this was the beginning of modern science. Because people realized that we, tiny little people on a small planet can do experiments with apples and discover truths that are valid everywhere in the universe. Distant galaxies, and any time in the universe, in the very early universe, upon its creation, we find universal truths that are valid everywhere and at all times just by doing experiments in our labs in this very small, around the small Earth for a limited amount of time. This was very liberating. It showed that, yes, we can think about celestial phenomena, and it started the explosion of modern science. And this recipe, Newton's recipe of unification, was repeated at least twice. First, Maxwell in the 19th century showed that electricity, magnetism, and light are all related. They are described by one set of beautiful equations, Maxwell's equations. And then in the 70s, the people figured out a way to unify the electromagnetism of Maxwell with the weak force. Again, weak force is something that causes radioactivity. And so there was the unification of electromagnetism and the weak force into the so-called electroweak force, which was completed theoretically in the 60s and fully discovered and confirmed by several colliders, including the LHC. Now that we would like to repeat this success to the other forces of nature, in addition to the electroweak and the nuclear force, in addition to the electroweak force, We have the nuclear force, the so-called strong force or nuclear force that keeps an atomic nucleus together, and then the force of gravity. So we would like to unify all of them together and into a grand unified theory. And this proves extremely difficult. This is an outstanding problem. And there are ideas on how to approach it, but and I'll talk about it, but it's very challenging for the reason that I told you before when I was raising my arm and pointing out how much weaker gravity is than electricity. So for example, if you compare the electrical force and the gravitational force between two elementary particles, let's say an electron and a proton, you find out that the force of gravity is 40 orders of magnitude smaller than the force of electromagnetism. This means, this is an astonishing number, so this means electricity is 1 with 40 zeros times stronger than gravity. So then, if two things are so different numerically, how can you stand a chance to unify them into one entity? So that's a huge problem. And there are about 3 attempts on this. These people have been thinking about since the 70s on how to do it. There are 3 types of approaches, and they have nice names like supersymmetry and compositeness. I will talk about only one of them, the third one, because you can see it envisages with a geometric picture. You can see it with a picture and understand it without any math. And this is called the theory of large extra dimensions. So for the theory of large extra dimensions, the basic hypothesis is the following. Imagine, so this is a two-dimensional piece of paper. Imagine that our universe is constrained to that this two-dimensional paper represents our three-dimensional universe. So think of the surface of this piece of paper representing the whole universe. Okay? And imagine that in addition to the space, to the universe, to the 3 dimensions of the universe, there are additional dimensions that we have not yet seen, we have not yet observed, that are perpendicular, they are represented by the height. So the vertical direction is a new dimension, and the horizontal directions on the surface of the paper are the familiar 3 dimensions. Furthermore, imagine that all the things we are familiar with, namely electrons, light, everything that atoms, etc., reside strictly in the 3-dimensional space, just like we normally imagine, except for gravity. Imagine that gravity that is not constrained to 3 dimensions, but is spreads inside the extra-dimensional space. If that is the case, then gravity, the strength of gravity, gets diluted by spreading in the space of extra dimensions, and therefore it becomes smaller. So gravity becomes weak because it propagates in extra dimensions, and the best analogy of this is the flow of a river. Just like the flow of a river weakens when the river splits into tributaries, when it spreads in extra space. Similarly, because gravity spreads in extra dimensions, it becomes weaker than electricity, even if, to start with, electricity and gravity had equal strengths. Because gravity spreads inside more dimensions, it gets more diluted. That's the idea, and of course this idea has a very very nice mathematical representation, extra-dimensional theories, and as well as string theory. And so this is one of the exciting things that people have focused on. Perhaps another analogy may help beyond the piece of paper. So imagine that you have a billiard table, a pool table. So think of the surface of the pool table as being as corresponding to our three-dimensional space. The billiard balls are elementary particles. Okay, so the billiard balls are, they can really be anything that lives in 3 dimensions, but let's think of them as elementary particles, let's say protons. And now we know from experience, when the billiard balls collide, although the billiard balls move in the two-dimensional surface of the billiard table, they produce sound which also propagates in the 3rd dimension, perpendicular to the billiard table. And that sound corresponds to gravity, gravity that spreads inside the in the extra dimensions. So that is the analogy. I have it here. So the sound waves correspond to gravity, and the billiard table corresponds to 3D universe. Billiard balls can correspond to elementary particles. This also suggests a possible signature of such a framework. When billiard balls collide, they produce sound waves. This means some of the energy of the billiard balls gets dissipated, goes into the sound waves. So if you measure the energy of the billiard balls before collision and after collision, you'll find out that some energy was lost to the sound wave. And that could be a signature that there is an extra dimension. And similarly, you can imagine doing this in colliders, or if you collide 2 protons, again, they can produce gravity that spreads inside the extra dimension, and that results in what's called the missing energy signature. So this is the fancy word is missing energy for large extra dimensions. So this is one of the possible signatures, and in general, in such theories, you can produce not only gravity in the extra dimensions, but other particles, strings, etc. Another test of extra dimensions, which in fact started from the late 90s at Stanford, is the following. All of you are, all of you know about Newton's law of gravity, so the force between 2 objects drops like the inverse square of the distance. Okay. Now, if you have extra dimensions, then if you have, let's say, one extra dimension, this Newton's inverse square law becomes an inverse cube law. It changes. So if there are extra dimensions, let's say that are 1 millimeter in size, and you bring 2 particles close together, closer than 1 millimeter, then you'll find out that the inverse square law becomes inverse cube law. And such deviations have been looked for. This is a diagrammatic of the Stanford experiment, but essentially the idea is very simple. You take a ball here that is on a diving board. So here is a diving board. This is this cantilever, and you put a test mass, a mass there, and underneath that mass you take another mass and you start oscillating it. And you oscillate it cleverly so that the rate at which it goes back and forth matches the rate at which the diving board likes to go back and forth. And that way you can excite big vibrations of the diving board by moving a mass at the right frequency, or in the right way. So experiments like this and others, as now there is many such experiments around the world, have searched for extra dimensions. They haven't found any yet. The present limit is that if there are extra dimensions, they have to be less than 40 microns. I should point out that the distances over which these experiments are done is on the scale of tens of microns. Now, this is this is shorter than the width, not the length, the width of human hair. Okay, so this is how amazingly precise small-scale experiments you can do these days. And these experiments, of course, are planned to be improved in the future. Now, I want to transition. Excuse me. Now, to how the presence, so where do we stand now? We stand with one way to explain the weakness of gravity is to introduce extra dimensions. Now, again, imagine that we have extra dimensions, so the vertical is the extra dimension, and this is this indicates the extra dimension. We can have one universe there. But extra dimensions has a lot of space. If you admit the idea of extra dimensions, then there is no reason why there should be only one universe there. You can fit another one. Here it is. You can have two parallel universes. Or you said it. You're a theorist. Or three or more, or you can have a book. This is a book, all parallel universes. And the interesting thing about this book, so these can all coexist in the space of extra dimensions. And the interesting thing about it is you can have different writing. Each page can be different. Each page can have a separate story. What does this mean? This means that each parallel universe can have different laws of nature. So having extra dimensions automatically implies the possibility that you can have parallel universes. And in fact, it's unreasonable not to think that we are the only thing. If there is extra dimension, it's only us, and it's a very self-centered view, which has been proven wrong over and over again in our universe. Every time we thought we were unique, we proved not to be unique. Each one of these universes can have different laws. This universe may not have a photon, maybe this has nothing, this is etc., etc. So they can be very different than ours. So it seems like the idea of extra dimensions is creating a tension between the principle of minimalism and the principle of plenitude. Minimalism would suggest one universe, plenitude many universes, and in fact, a famous mathematician, Leibniz, suggested that there should be the perfect world contains all possibilities. You can tell from their hairstyle that they had slightly different views of, you have the monastic view of fashion and the opulent view of fashion. And this was reflected in their philosophies. So, now, it's not the first time we face this. Until around 1600, most people, definitely not all, but most people, thought that there was only one solar system. And it was very special, that was the whole universe, it was made just for us, we're at the center, etc. And in fact, it was considered, as we know today, now we know that there is in fact 10 to the 20, one with 20 zeros, solar systems in the universe. So, of course, this is a very natural idea now, but it was somewhat controversial in 1600. And in fact, the person, again, another priest called Giordano Bruno, who wrote a book about it, claiming that the universe is infinite and it has innumerable worlds in it, That was considered blasphemous because we were no longer special. We were not, God's children, or the only children, blah blah. And the poor guy was burned at the stake. Thanks to this, Galileo was saved because Galileo became a bit more conservative in expressing his beliefs openly. So now having many solar systems has tremendous consequences in two things. First, it changes the way we think about our solar system. For example, there are no PhD theses written today to explain mathematically the distances of the various planets. That would be ridiculous. There is, because there is nothing special about our solar system. There is nothing special about the Earth-Sun distance. It's a historical accident. The other thing is, it points to something called environmental selection. I want to dwell on this. So, one solar system, essentially saying what I said before. In fact, Kepler, who was a very smart guy, built a theory of nested platonic solids, and then there were spheres separating each sequential from the tetrahedron to the cube. There was a sphere, etc., and the next solid has the sphere. And the radii of the sphere were related to the distances of the planets, etc. Very elaborate theory. Didn't work too well. Maybe 10%-ish on most things. There were only 6 planets known. Anyway, but it's clearly not a good idea to work on this. If you want a job, when we know that there is 10 to the 20 solar systems. The other thing is even deeper. It has to do with what that if you have one solar system, there are some mysteries. For example, let's say ours is the only solar system. There are obvious questions like, what about how come the Earth-Sun distance is just right so that it's not too hot and it's not too cold? So it's friendly for our existence. Or, much more complicated, how come the chemical composition of our planet, etc., is just right to allow for our existence? It looks like either someone cared a lot and put us together very carefully, put everything together to make sure that we exist, divine intervention, or there is a second possibility, environmental selection. And indeed, we all that is the point of view. If you have many solar systems, then environmental selection can account for all of these accidents, whether it's the chemical composition of the Earth or the distance between a planet and the star, etc. So it allows you for a new way to reason, which is not quite the usual physics equations, but still very powerful. Now we have a very big problem, which I mentioned before, the cosmological constant problem, which, as I said, says that the universe shouldn't be more than a millimeter given the value of the dark energy that we expect in the standard model. Again, the only way to solve this problem without any revolutionary idea is to add another parameter to the theory and cancel 2 parameters to an incredible precision, 100 decimals. However, if you have many universes, the solution again becomes environmental selection. Most universes would be too small for us, but if you have enough universes, they have enough different dark energy content, then some of them, like this one, will grow to become as big as ours. And so this is the only known solution to the cosmological constant problem. It relies on having a multiverse, but the moment you accept the idea of extra dimensions, accepting the multiverse is one small step. Since the space is already there. Okay, now I don't have that much time, so I'll go rapidly over this so that Emily doesn't get too angry with me. So this essentially demonstrates the following important connection, that And that in string theory, this picture, the sequence of pictures, explains that in string theory you get multiverses because the extra dimensions have to be curled up in a small space, and there is practically an infinite variety, an infinite number of ways to curl up extra dimensions in a small space. And this gives rise to each one of these corresponds to a different universe with different properties. And one very important thing that I'll come to, the existence of this complex extra-dimensional space with all the holes, etc., implies the existence of extra particles, which have fancy names like axions, dilatons, moduli, etc., that characterize properties of the extra dimensions, the extra-dimensional geometry, and are things worth looking for. These are potential signatures. Seeing some of these things could be signatures for the existence of these extra dimensions. And this could be the analog. So looking for such particles could be the analog of Galileo's telescope, which allowed us to look and eventually to discover that there are other worlds out there, there are other solar systems, other galaxies, etc. Okay, so here, this essentially summarizes what I just told you. The consequence of multiverse can explain, it's the only known explanation for why the universe is big, and it can give rise to a bunch of particles that we can look for. And these particles can be looked for in many ways. These particles can be the dark matter, or they may behave like waves or like particles. But one thing for sure, the properties are such that most of them cannot be seen in colliders. So they are not things to be looked at colliders. You need to go to small-scale experiments. Lots of such small-scale experiments have been done, are being done, and are being proposed. They have fancy names depending on the fad and the appetite of funding agencies. They are called, as time evolves, different things: small-scale science, tabletop experiment, precision frontier. Lately, quantum sensor is the fad. In a year or two, probably AI-assisted searches for new physics will be the titles. A lot of ideas. If they are not the dark matter, we can just see them because these extra particles can mediate forces. And one of the most exciting things is that even the very existence of these particles implies if the particles are light enough, they can be produced by rotating black holes. So rapidly rotating black holes can create these particles, and which can create a cloud of particles around it, and these clouds annihilate into gravitational waves, which can be seen in advanced LIGO, which is the gravitational wave detector that in 2015 for the first time discovered gravitational waves. Now, if the particles are the dark matter, they can also be seen in different ways. If the particles are heavy enough, they behave like billiard balls, like true particles. So they can collide. These are like billiard balls. They collide with a detector and deposit energy in it, for example, and that's how you can see them. If they are waves, then there are several signatures that they can have that I will. For example, they can manifest themselves like spurious magnetic fields that various experiments are looking for, or they can change the fundamental constants of nature. So this wave dark matter can change the fundamental constants of nature. So it particularly can change the sizes of atoms. And since solids are made out of one atom after the other, after the other, after the other, like soldiers, if one atom breathes or changes its size, the whole solid will breathe and change its size. So you can look for such signatures. They can also affect atomic clocks. I don't have time to explain this. And finally, one thing that is very exciting, we're excited about it now, is that they can interact coherently. And here is what I mean by this. So imagine this blue dot here is a dark matter particle, and orange dots are atoms. Okay, so if a dark matter particle is like a particle, is like a billiard ball, it can collide with any one of these n atoms. So the rate of interaction scales like the number of atoms. The more atoms you have, the more likely you'll encounter one. So the interaction rate with the detector made out of these orange atoms is proportional to the number of particles. Turns out if you have a big wave, then a big wave can interact at the same time with all the particles. And that can give rise to a scaling that is not proportional to n, but to n squared, the square of the number of atoms. Since the number of atoms can be a big number, like Avogadro's number, 10 to the 24, there is a huge advantage in having the second case. And in some cases, you can even realize it. For example, there is a famous particle that actually exists from Big Bang relic neutrinos. Depending on the detector, a relic neutrino can behave as either a particle or a wave. And if you can have a detector, a special state of detector, where the neutrino interacts like a wave, it makes a huge difference. A neutrino that behaves like a wave interacts, let's say, once every second with a 10 centimeter detector. The same particle with a slightly different detector, where the neutrino doesn't act like a wave, interacts once in the age of the universe. So there's a huge one rate that cannot be observed. It only happens once in the universe. This happens once every second. So that's how different. So now I'm ending with a brief summary. We started out pointing out that we transition. Here is the era. Here is energy as a function of time. Okay, and actually time starts around 1960. I could extrapolate this earlier. But the energy of colliders, red represents proton colliders, blue is electron colliders. Okay. As you see over the years, in fact, you can go back to 1920s, etc. Over the years, there has been an exponential growing energy. Lately, that exponential has leveled off. It has leveled off because of technological reasons and practical reasons, cost. And this leveling off is expected to continue for at least 3 decades. So the high energy frontier, going to higher and higher energy, which is the main strategy we've been using to look for new physics, is being saturated. If you compare this to what happens in the high precision, for example, frontier, there are several such plots. So here is the uncertainty, fractional frequency uncertainty, again, as a function of time. And black is microwave clocks, red is optical clocks. What do you see here? Optical clocks had the stability of 1 part in 10 to the 13, and now it has gone to 1 part in 10 to the 18. What does 1 part in 10 to the 18 means? It means that this clock, in the whole age of the universe, misses a second. loses a second. 1 second in 10 to the 18 seconds. Okay, so if you have a date, you can be precise. You set a date at the beginning of the universe. You adjust your clocks together. Say, we'll meet in 10 billion years. You meet in 10 billion years with an accuracy of 1 second. So it's incredible, and it's, in fact, by now it has gotten better, and I'm not showing it here, and this continues. This means that you can do exceedingly precise measurements. If two quantities are off in the 18th decimal, they'll behave differently. And that's how, for example, you can look for oscillating dark matter. Two clocks will be a little off, but if they're off by one part in 10 to the 18, because they are affected differently by oscillating dark matter, you will see it. And so the high precision frontier is anything but saturated. It's still progressing exponentially. And in the next few years, we've been cultivating exciting interfaces between new physics and fields. These fields are experiencing exponential growth. And as I said, these fields involve much smaller labs, people, money, resources in general. Essentially, they've been building for several decades while the colliders were going on. These people were not sitting still. They were doing really miraculous work. In fact, if you look at the Nobel Prizes the next 25, 30 years, it's full of such progress. So new tools fit the open question, the open questions. The open questions being, what's the dark matter? Is there any evidence for the multiverse, these particles, axions, dilute, moduli, etc., for example? So let us end by contemplating, what if we discover the multiverse? Find evidence by finding several of these particles that the multiverse predicts. Okay, so philosophical thoughts. We started several centuries ago. We believed that we were at the center of the universe, the Earth. We were very special, we were right at the center, and everything else revolved around us. Then we found out that around 1600, well, that's not quite true. Actually, the sun is at the center. We are sort of the third planet over. Well, it's not so bad. It's still one solar system. We are still sort of special. And then we found galaxies. We say, wait a minute. Our galaxy is sort of, I forget, a third or two-thirds of the way out from the center. It's one of 10 billion galaxies. And it's not even at the center. We're sort of less important. Then we found out that there is 10 billion galaxies. So, and ours is not at the center, because there is no center in the galaxy. It's very democratic. Now we are contemplating the possibility that our whole universe may be less important than a speck of dust in a vast multiverse.